Hello. So previously we have seen some models of the active medium. Um, so the active medium could contain atoms, molecules, a periodic arrangement of atoms like in a solid. Uh, all of these comprise of essentially two levels effectively within which transitions of the electron happens and wherein the electron can either take in energy and make a transition or come down and give out energy. And it is this coupling that we are, of course, interested in. What I want to do now is just like we dealt with the field independently and we looked at field in a cavity, in a similar manner, I will look at the simplest model of the active medium, which I can talk of in terms of just a two-level atom. So what I'm doing is I know that there is an underlying complexity to the atomic structure, but I'm ignoring everything else, but keeping only the relevant states. That is, uh, I'm interested in a radiation that is close to resonance to the two levels of the atom. I have two energy states. The ground state is denoted by 1, the excited state by 2. And electron can either be in the ground state or in the excited state. Even though the atom has got much more complex atomic structure, we are only interested in this subspace within the atom, wherein we are talking about the two levels involved, which are resonant or close to resonance with the radiation field that we are interested in. So in this two-level system, you can have, for example, so what are the possibilities? I'm looking at a radiative interaction of the atom with light. I can come in with a radiation which is nearly resonant. So this is the energy H cross omega, where omega is the angular frequency associated with the radiation, and H cross omega 21 is the atomic energy. So few things can happen when the atom in such a situation. So what we can have is actually absorption. We can also have stimulated emission and also spontaneous emission. So essentially these are the three radiative processes that I will worry about, and see what lessons one can learn out of this. Clearly, to undertake this exercise, I need to take recourse to quantum mechanics properly, but I will not do that. What I will do is to give you phenomenological arguments that basically govern this atom light dynamics. So I'm going to take recourse to something called rate equations. So I'm just going to write down rate equations and support them on the basis of what we expect the reasonable physics behind the phenomena. Suppose I have got n atoms per unit volume, right? And then because I have made something called the two-level atom approximation, implies that there are some of these atoms will have electron in the ground state, and some of these atoms will have electron in the excited state, and this is my total collection. What I have is this total constraint that n1 plus n2, that is the number of atoms in the ground state and the excited state, add up to the total number of atoms. So what I'm doing now is writing down the time dependence of these. So to begin with, let me look at dn2 over dt, which is the rate of change of atoms in the excited state. So we know that spontaneous emission can actually decrease the number of atoms in the excited state, and the spontaneous emission, one can talk of a rate. I represent that rate of spontaneous emission as A21, right, with a negative sign, and it depends on the number of atoms in the excited state. So clearly the number of atoms in the excited state decrease with the rate spontaneous emission rate A21. Similarly, because of stimulated emission, right? So the number of atoms in the excited state come down, right? And this is given by stimulated emission, as you know, is a quantity that is proportional to the number of atoms in the excited state as well as the photon flux, right? Here, sigma is what I'm going to talk about in a few minutes. Sigma is in this case, the stimulated emission cross section. The sigma has got the units of area. Essentially, it's the same as scattering cross section, and I will talk about it soon. The other phenomena that leads to change in the excited state, number of atoms in the excited state, is absorption, right? So where absorption is given as, absorption of course depends on again the same cross section for absorption times the number of atoms now in the ground state times the photon flux, right? So um, let me define what is my photon flux. Photon flux is number of photons impinging on the atom per unit area per unit time, right? That's my photon flux. So now let's look at and make sure that our units are correct. So on the left hand side, you have N2, right? N, which has got the units of uh, per unit volume, 1 over volume, right? Because it's number of atoms per unit volume. And you know that A21 is the rate of spontaneous emission. It's again 1 over time, right? This is a spontaneous emission rate. And we have again N2 times sigma is going to be 1 over volume. And then essentially I'm going to have the photon flux as 1 over area times time. And you see that units of area. So that area gets cancelled. And what you get is basically a quantity which is 1 over volume time. Right. So this is how my the number of electrons in the excited state change. Now let's write down the rate equation for the ground state population. So I'm using this word population. It's a technical term in atomic physics uh, and quantum optics. I might also use the expression population, which simply implies the number of atoms in that particular state. So the the population in the ground state changes as dn1 over dt. That's the rate of change of the ground state population. And this again depends on these three processes where the ground state population actually increases because of spontaneous emission, right? And it's proportional to N2. It is the it is essentially what is lost in the excited state is what is gained by the ground state, right? Similarly, uh, the stimulated emission process will actually lead to increase in the number of atoms in the ground state. That is given as plus sigma times N2 times phi. There's a stimulated emission which is bringing the atoms from the excited state to the ground state. And you have absorption process which is actually decreasing the number of atoms in the ground state. Hence that is given as minus sigma times N1 times phi. In general, one could have a situation where there is a finite decay of this atomic population to other states within the atom, right? For example, I could talk of a rate of decay as gamma 1 and gamma 2, which could be the rates of decay from the in the of the ground state and the excited state respectively. So I can maybe add a term in general minus gamma 1, gamma 2 N2, which tells me the decay of the first equation. Similarly, minus gamma 1 N1, which tells me the decay of the second equation outside these two levels. Because as we know, the atomic structure is much more complex. Such processes also are very much present. Of course, what we are saying is that this gamma 1 and gamma 2 are much, much smaller than the corresponding rates, for example, the spontaneous emission rate. And hence, one can essentially ignoring gamma 1 and gamma 2 is actually leading us to something called the two-level atom approximation, right? Because this is what ensures that the electrons do not go out of these two levels, and they stay put within these two states themselves. So that is essentially what is the two-level atom approximation. All right, we are going to solve these set of two equations and see what we can learn from it. Before I do that, I want to actually talk about this cross section. So sigma, in one situation I have used it as the stimulated emission cross section, and in the same equation I use the same term as absorption cross section, and the same thing in the second equation. So this equality of sigma, right, that sigma absorption being equal to sigma stimulated emission, right? This equality between the two is actually governed by quantum mechanics, and this is what is called as microscopic reversibility. So what one is saying is that essentially there is a certain transition that is involved. There is a coupling of the atomic dipole moment to the light, and whether you are going from excited state uh, to the ground state or vice versa, the coupling of the field and the atom is irrespective of where you begin with, and these two processes are exactly identical at the very microscopic level, and hence we do not distinguish between the two. Right. So now let us spend some time on this business of cross section itself. In general, these are all family of something called scattering cross section. So the way one defines cross section sigma is essentially it's a ratio. It's a ratio of, for example, if I'm looking at absorption cross section, then it is simply energy absorbed per unit time per atom in level 1, right? It's my ground state, divided by the incident radiation flux. So essentially it is giving me, it's a ratio of these rates. So let us figure it out. What is in the context of what we are looking at? So the amount of energy absorbed is h cross omega, where omega is the frequency of the field. And let me call R12 as the rate of absorption. That is absorption per unit time. And I'm dividing this by the incident radiation flux, which is basically the intensity of light that is coming to me. So intensity is given as, for intensity in free space, if I have electromagnetic wave, epsilon naught is the permittivity of free space, c is the velocity in free space, and e naught is the amplitude of the wave, and hence intensity is amount of energy per unit area per unit time. This also can be written in terms of photon flux. Remember, photon flux was the number of photons per unit area per unit time. So if I multiply this with energy, then you see that what I have is intensity, which is energy per unit area per unit time, or in other words, this is power per unit area. So my intensity can be written down again here as half epsilon naught C E naught square, right? where E naught is my amplitude of the electromagnetic plane wave that is incident on my system. R12, which is my rate at which absorption happens, that of course clearly depends on this business of being on resonance or not, right? We have just seen earlier that the interaction between the atom and light is maximum when it is on resonance. So you see that one can write down this rate of absorption. And by the way, these can be derived from first principles using quantum mechanics. I'm simply stating these results, and you can you can take it as granted. And if you want to dwell on these, you can look at our textbook where you would find a detailed description of how this is derived. So absorption rate essentially can be captured by uh, this particular quantity where E is the charge, R12 or R21 if you like. This is the dipole moment associated with the E times R. That was the dipole moment associated with the transition of atom going from 1 to 2, right? And the dipole moment needs to be dotted with the polarization of the electromagnetic field. And so that's my amplitude of the field. And this is divided by H cross. So the mod square of this essentially governs the coupling between the atom and the field. And you see that there is a notion of the resonance wherein, remember, we had introduced this notion of a beta. So there is a beta by 2 times omega 21, which is my resonant frequency, minus omega square plus beta square. Remember, this is related to the line shape that we talked about. This is the absorption cross section that one can write down related to this interaction between light and matter. Let me just quickly qualify what I mean by this term. This is a little bit of quantum mechanics. When you're looking at R21, what you're looking at basically is you're looking at a wave function describing the ground state psi 1, and you're looking at the so-called interaction Hamiltonian, which basically is so E times R12 is minus R, right? That's my dipole moment. And this is computed, uh, this interaction takes the atom from the ground state to the excited state. And so ER12 is essentially this object. So when I'm looking at, mod square of this or something, this is my so-called the interaction Hamiltonian, which essentially it captures this um, transition probability of going from one state to another. And I think for simplicity, we can just replace this whole thing as uh, dipole moment of the atom, right? So we will use this short form to capture this. Right. So clearly you can see that my the rate at which energy is absorbed depends on how close I am to the resonant frequency. And of course, you know that I can only couple energy only if I have a finite decay in the system, and that is captured by this beta. Right. So if I now put all of this together, I can get sigma to be of the following form, right? Uh, Clearly, sigma is a function of frequency, so one can write this out as d square omega. You see that my E naught square, there is a E naught mod E naught square and mod E naught square both in the numerator and denominator, which gets cancelled. And what you are left with essentially is this 3 epsilon naught C H cross. You can check the algebra for yourself. And this is beta divided by omega 21 minus omega whole square plus beta square. To be honest, I should write my sigma to be a function of frequency, right? So this is how the absorption coefficient actually looks like, and this is same as the stimulated emission coefficient. Now, when I'm looking at atom in which the only broadening process, right? This, remember that beta was the width of the absorption line shape, and the only broadening process is spontaneous emission, then my beta can be is actually equal to A21 by 2. One can have other contributions to beta, right? But if the contribution is from spontaneous emission only, then this would be the form of the decay. So now you see, if I'm looking at resonance, right, then you see that sigma at omega 21 equal to omega, right, at omega equal to that, it's at resonance. This simply becomes d square omega 3 epsilon naught c h bar. This is my prefactor, and omega equal to omega 21, that goes to 0. So essentially what I have is 1 over beta contribution, and that is simply 2 by A21, right? With A21 is my spontaneous emission uh, line width, or the rate of spontaneous emission. Such a system uh, or such a broadening mechanism is also what is called as natural broadening. And you see, all systems would suffer this. We will come to broadening mechanisms probably in the next lecture. What is the line shape governing the light atom interaction? So in this situation, it is a Lorentzian clearly, and the line width is only dictated by the spontaneous emission rate. I can give you just a little bit glimpse into uh, a fantastic result that one has. So for example, you can just take it for granted. A21 itself has been calculated using quantum electrodynamics, um, and an expression has been obtained for it. So I will not go into that process, but I'll give you the formula of the expression for spontaneous emission, and you can just take it as it is and see what are the consequences of this. So the A21 formula, this is coming from QED, or also known as quantum electrodynamics, and this simply is the dipole moment between the states 2 and 1 square, right? Omega 21 cube divided by 3 pi epsilon naught h cross by c cube. So this is the rate of spontaneous emission, which is derived independently, right, using quantum mechanics, right? So what I'll do is I will plug this back into this equation, and I will check out what is the nature of my absorption cross section. So sigma now at, for example, delta, so equal to 0. By delta, what I mean is delta is a quantity which I state as detuning. It is a technical term which simply implies the mismatch between the atomic frequency and the optical frequency. So that is my delta. This by definition. Uh, so clearly sigma is a function of my delta, and delta equal to 0 implies I am at resonance. There is no the atomic resonance and the optical frequency is tuned. There is no detuning to each other. So at resonance, and we will see what we get. So you have d square. Of course, this omega is same as omega to 1. So there is 3 epsilon naught c h cross uh, times 2 into 3 pi epsilon naught h cross c cube divided by d square again times omega cube again. Is that correct? So this part, this second expression is coming from uh, my this result, and I am simply plugging in the value for a21, and I will see uh, what that gives me is that my d square gets cancelled, my omega, and this becomes omega square, uh, 3 epsilon naught h bar c and c square. So essentially what I get is 2 pi c square by omega square, right? And we know that this c square by omega square is nothing but c square by 4 pi square nu square, which simply is lambda square over 4 pi square, or this quantity is simply lambda square over 2 pi. So this is a quite a fantastic result. What it is telling you is that the maximum cross section what you get is independent of the atom. What matters is the size of the wavelength. Now let's understand this. Remember that the atomic size are of nanometers, and my resonant transition, for example, let's look at in visible, is about hundreds of nanometers, right? So this quantity will be about 10 to the power of minus 14, right? Meter square, hundreds of nanometers for that matter. Okay, so let's consider 500 nanometers. So this is 25, and what I have is 2 pi, which is sitting there. So this essentially is 10 power of minus 14 meters square. This is the area associated with the interaction between the light and the atom, whereas the atomic area per se is about 1 angstrom square, right? This is my atomic size. So this is 10 power minus 20. If you look at the ratio of this, so you see that a light on resonance. So one is thinking of these atoms, uh, think of this atom, and then what is happening is that when my light beam is coming to an atom, where this light beam is on resonance with this, the atomic size appears to be a million times larger than the actual size of the atom, right? Because you see this ratio is about 10 power of 6. So a resonant radiation interacts extremely strongly with the atom because of this apparent large cross section area. Essentially, imagine that if you are looking at a collision between two billiard balls, imagine that the billiard ball has radius r. So one billiard ball is of radius r, and imagine the second billiard ball is identical again of radius r. Then you would see that within this 2r radius, right? If the distance between the two balls is within this 2r radius, you will see that there will be a collision. So hence, the collisional cross section from two identical balls will simply come out to be pi times 2r whole square, right? So this essentially comes out to be 4 times pi r square, which is what is the collisional cross section for simple billiard balls. Whereas when you look at these atoms, And that is what makes this result so fantastic. So when you're looking at atoms, you are seeing that the atom interacts resonantly, and hence the cross-section area increases by a factor of roughly, 10 to the power of 6. That's an extremely large increase because of the phenomena of resonance. So that's the important thing which I wanted to convey with regard to cross-section. All right, so now let us get back to our original task, which is to try and solve these equations in various limits. So I'm coming back to my original discussion. So what I will do is, rather than looking at both the equations, I will eliminate one of them. So for example, let me eliminate N1. Remember that N1 plus N2 is my total number of atoms. So I can as well replace my all my N1s in terms of N2s and capital N, right? So I can write down my N2 dN2 over dt in the following form. I have minus A21 N2. I have minus sigma, which is a function of frequency, times phi times N2 minus N1. Please go back on the top and look at these equations. And this N1 I am replacing by N minus N2. That simply gives me uh, the following form, which is, you see that the second term essentially is a constant, right? So I can write down the solution of this equation exactly, right? This is a first order equation with just one coefficient. So you see that I can write down my N2 as a function of time in the following form. So my N2t is simply N2 at time t equal to 0 minus total number of atoms times sigma times phi. I am dropping the frequency delta dependence. I will come back to it later. A21 plus 2 times sigma times phi, and this is exponential minus A21 plus 2 sigma phi. These terms keep coming together, right? And we have to ensure that we satisfy the initial condition, which is that at time t equal to 0, we get n to 0. That would mean I have to add this constant, which is, right? So this is my central result, and I'm going to analyze these in various contexts. Let me give it a number. So let me call the first two equations as equations 1 and 2. This is my equation 2, and this equation, which is my the solution of those two equations, is equation number 3. So I'll keep using equation number 3 in various contexts. Right. So let me look at it in a particular regime. So look at the simplest of the regimes. So the first regime I want to look at is when my photon flux is 0. Imagine my phi is equal to 0. That is, there is no input photon flux, right? So what do you get here? If I put phi to 0, you will see that equation 3 will give me that my N2t will simply give me the first term, which is N2 0, whatever be the preparation N2 0. And as t tends to infinity, so because my sigma is 0, my exponent here for the decay is simply exponential minus A21 times t. And you see this, the second constant term, because phi itself is 0, it does not simply contribute, right? So this becomes my result. Is it reasonable? Indeed it is. What it is telling you that if I prepare the atoms in the excited state, remember that my level 2 was the excited state. If I prepare the atoms in the excited state, they would simply spontaneously decay. And that exponential decay is neatly captured in this expression. You can have the second situation where I'm looking at a weak field excitation. I'm calling this as weak excitation. This corresponds to the fact that my sigma times phi, I have to uh, compare apples to apples and not apples to oranges. My sigma phi is much smaller than the spontaneous emission rate. Remember, sigma times phi is telling me the amount of photons impinging times, of course, the cross section. It is giving me a rate, and I'm comparing this rate, the impinging photon rate, to be much smaller than the spontaneous emission rate, which is the natural time scale of decay or rate for my atom. So in the weak excitation limit, clearly my sigma phi is much smaller than A21. So again, let us look at equation number 3 and see what it tells you within this regime. Clearly, when I'm looking at weak excitation, I'm basically looking at atoms in the ground state. That would mean that I can set my N20 to be 0, right? Because all my atoms are in the ground state, so the excited state is essentially empty, right? So in that situation, I see that my N2T in the weak excitation regime is simply the following. And clearly there is a, you can see that clearly there is a denominator which is A21 plus 2 sigma phi, and because A21 is a dominant quantity, I can ignore this 2 sigma phi contribution. So what I get is basically n times sigma phi divided by A21, and there is a 1 coming from the last constant minus coming from the second term, which is exponential minus A21t. So what it is telling you is that as t tends to infinity, for example, in the steady state, remember that sigma phi is much smaller than A21. So what you have is a fraction of atoms in the excited state, and most of the atoms basically remain in the ground state. And the fraction of atoms simply depends on the photon flux. This is a steady state picture. So remember that it is we are still talking about a dynamic interaction where you see that sigma times phi is a constant. Again, here the photon flux is a constant. So I'm not looking at it as a time dependent phenomena, but I'm looking at either the photon flux is there or not there, and I'm looking at now level at which the photon flux is. So it could be weak excitation that tells me that very few atoms will go to the excited state, will remain in the excited state, and most of them will occupy the ground state. The next regime of interest is the strong excitation. So again, let me repeat myself. I've ensured that my photon flux is a constant in time, and hence I am looking at it as a constant parameter. If my photon flux itself was a function of time, I'll have to integrate this more carefully. Okay, so for in the strong excitation, obviously I need to reverse this above condition. Now my sigma phi is much greater than A21. Now if I look at my N2T, I see this amazing behavior. I'll keep it as whatever is the initial preparation. After all, I'm coming with a strong field. And if you look at this ratio now, right, this ratio clearly is such that I can ignore the A21 in the ground state. That would mean the sigma phi gets cancelled and I get basically n by 2, right? So I can write down this as n20 minus n by 2. And of course, this whole thing decays quite strongly because the decay coefficient is 2 sigma phi, right? Which is the dominant coefficient here. So larger the photon flux phi, greater is going to be, faster is going to be this decay. Plus you get this constant term, which is simply n by 2. So you see, as t tends to infinity, that is in steady state, what would happen is that my n2 t tends to infinity steady state is going to be simply n by 2. This should be a very illuminating result for us because it's telling us something very, very fundamental. It is telling you that however strong the field you can come up with, the best you can do with the atom is equalize the population between the ground state and the excited state. The stronger is the field that impinges on the atom, faster it is going to reach this state of equalization of the population. What it is telling you microscopically is that if there is a larger amount of population, let's say in the ground state, then absorption will dominate, right, in comparison to stimulated emission. And if there is a little larger amount of population in the excited state, then stimulated emission will dominate to bring the atom in the ground state. The interplay between these two phenomena will ensure that in the steady state for extremely strong field, there is neither absorption nor stimulated emission, or they both balance each other so as to make the system completely transparent. This, by the way, is what is known as bleaching, or the what we are doing is basically saturating the atomic system such a way that it no longer absorbs the radiation. Radiation simply passes through it apparently without any interaction. So it is very important for us to understand that by merely increasing the amount of radiation, we are not going to achieve population inversion, which is required for us to obtain lasing. The second important thing that we learn is that even if we create population inversion, any manner whatsoever, generation of a strong field will do is basically destroy that population inversion and equalize the population between the ground state and the excited state. It is for this reason, is what I was saying, that our gain, or for that matter, there is no laser which can simply have a runaway kind of a situation where the light keeps generating without any limit, simply because as the light becomes stronger and stronger, the population inversion that you create is essentially wiped off and you get equalization of the population. So another aspect of strong interaction is this notion of power broadening. So let's look at the equation for N2T, and let's look at the situation where you're looking at the steady state result. So clearly in the steady state, the exponential decay will take care of the first part. What remains is that constant at the end of equation 3. So what we get, that is my N2 at t equal to infinity, that is the excited state population, is simply total number of atoms times sigma, which is a function of delta, times phi divided by A21 plus 2 sigma phi. I can rewrite the ratio of atoms in the excited state to the total number of atoms, that is N2 by N. We just rewrite the same equation as simply sigma, which is a function of the frequency difference, times the input photon flux, A21 plus twice. So now let us bring down the explicit form of sigma and multiply that by phi. So you can do the algebra, but what you would get is basically sigma delta times phi, this product, which is by the way the same as the rate of absorption, will come out to be this quantity, which is d square, which is the dipole moment square, E naught square coming from the phi uh, divided by 6 h cross square times beta by del square plus beta square. So that forms the prefactor, and this is the explicit dependence on the frequency difference. So remember, delta is the detuning, which is the difference between the atomic resonance frequency and the applied field frequency. Let me just rearrange this in my expression here. So what I eventually get is the following form, right? So that is essentially the form for the uh, number of atoms in the excited state. Now, clearly, you would see that this almost mimics the Lorentzian distribution, where you have a constant. And if you look at the frequency dependence of this quantity, that is, if I am looking at the number of excited state atoms as a function of frequency, right, that ratio would typically look like a Lorentzian function, right, with some prefactor. And not just that, if I'm looking at the width of the Lorentzian, right, let's look at it graphically. What you would see is that I get a Lorentzian, and now you see that the width of this Lorentzian is no longer merely beta. So you see this beta square plus this intensity dependent quantity is what is determining the width. So what would happen is, correspondingly, at delta equal to 0, for larger values of this, you would actually look at a profile that is tremendously broadened and lowered. So this is the situation when my E naught square, that is my phi, is 0, right? This is the phi is finite, right? So you see that the amount of atoms in the excited state are actually going to be lowered because of this uh, clear Lorentzian dependence, uh, where the uh, where the line shape itself gets broadened because of this factor sitting here at the bottom. So essentially, what we get, full width at half maxima, is simply, two times. We can look at this bottom factor, which is beta square plus d square e naught square 3h cross square a21 square root, right? This is going to be twice. That factor is going to give me this full width. This is going to be my full width at half maxima. And this, right, I can rewrite in this form. It's 1 plus d square e naught square. I have missed a small factor of beta, so please correct it. I need to put a beta here, and there is a beta here as well. Right, so this becomes my new Lorentzian, whose width now depends on the intensity of the applied field, right? E naught square. And this is what is the notion of power broadening. So you can clearly see in our journey towards trying to obtain high powered outputs from lasers, it is going to come at a price. And the price they're going to pay is in terms of the line shape. The line shape is going to broaden. That would mean that the resonant interaction itself is going to decrease. And the early lesson that we have learned as that as you keep increasing the intensity of the light, what happens is, in strong excitation regime, what you do is basically equalize the population ground and excited state, and essentially that leads to a decrease in the population inversion that you might have to create to obtain lasing. So we have to keep these lessons in mind in order to obtain lasing as we go ahead in the course.